By the end of the 19th century, physicists believed they had the universe largely figured out. It was a place where physical laws were predictable, and light, above all else, was understood to be a smooth, continuous wave. This certainty was anchored by James Clerk Maxwell. His equations provided the mathematical proof that light was a continuous electromagnetic wave rippling through space. In this model, energy is distributed evenly across the wave. When light hits an object, it should behave like ocean tides hitting a beach, slowly and steadily transferring energy to every electron it touches. The math worked so perfectly that many scientists believed the great discoveries in physics were already behind them. To them, the universe was a finished house, and they were just checking the measurements of the rooms. But new discoveries began to complicate that finished house. In 1897, J.J. Thomson identified the electron, showing that solid metals are packed with these tiny, negatively charged particles. These electrons are held inside the metal by an attractive force. To pull one out, you have to pay a specific energy toll, a minimum requirement known as the work function. Physicists knew you could pay this toll with brute force. You could heat the metal to glowing temperatures or hit it with high voltage to knock the electrons loose. But Heinrich Hertz discovered an anomaly. You didn't need heat or high voltage. Shining a simple ultraviolet light onto a metal plate would also kick electrons right out into the air. This is the photoelectric effect. According to the wave theory, that light should act like a gentle tide, slowly depositing energy into the metal until an electron finally gathers enough power to break free. But when they looked at the laboratory data, that isn't what happened. The wave theory leads to a simple prediction. If you turn up the brightness, the intensity, of the light, you are hitting the metal with more energy. Therefore, the escaping electrons should fly out at higher speeds. This graph maps the results of that experiment. We are looking at the volume of electrons emitted, the current, measured against the retarding potential, which tells us how much kinetic energy those electrons actually have. While a brighter light does emit more total electrons, look at the x-axis. All three intensity curves converge at the exact same stopping potential. The speed of the individual electrons hasn't changed at all. Turning up the brightness doesn't make the electrons faster, it just makes them more numerous. The wave theory had no way to account for this. There was also the problem of time. If a light is extremely dim, a continuous wave would need to pool its energy for hours before a single electron could pay the work function toll and escape. In reality, the emission is instantaneous. Even with the weakest, dimmest light sources, electrons pop out in less than a billionth of a second. There is no slow buildup of energy. The transfer happens the moment the light touches the surface, which meant the wave model's core assumption was effectively dead. The final test looked at the frequency of the light, what we see as color. This graph maps the frequency of the light on the x-axis against the stopping potential on the y-axis. The data shows a hard barrier called the threshold frequency. Below this specific point on the x-axis, the graph is empty. If the light's frequency is too low, no electrons are emitted, even if you use a blindingly bright light for 100 years. If light were a continuous wave, intensity would eventually pay the toll. But the laboratory data was conclusive. The rules of classical physics no longer applied to the behavior of light. In the year 1905, Albert Einstein provided the explanation that classical mechanics couldn't. He proposed that light is not a continuous wave at all. Instead, it travels in completely discrete, indivisible packets of energy. He called these packets quanta, what we now call photons. Einstein's equation treats this as a one-to-one transaction. One photon hits exactly one electron. The photon pays the work function toll, and whatever energy is left over becomes the electron's speed. In this interaction, light isn't washing over the surface like water, it hits like a particle. This model fits the data perfectly. Brighter light simply means you are firing more photon bullets, which ejects more electrons. But it doesn't make the individual bullets hit any harder, so the electron speed stays the same. It also explains the threshold frequency. A higher frequency light means a more energetic photon. If the frequency is too low, the individual photon bullet lacks the energy to pay the work function toll. The transaction fails immediately. And because it's a direct collision between two particles, there is no time lag. The energy transfer is as immediate as a cue ball hitting a billiard ball. While these findings resolved the conflicting graphs, they also forced physics to reckon with a contradiction. If Maxwell's waves were still required to explain shadows and rainbows, and Einstein's particles were now required to explain electricity, light had to be both. This was the moment the old rules of mechanics broke, revealing a universe where energy only moves in discrete, indivisible chunks.